Okay, here we're going to look at question 8. This is two more examples of telescoping series, okay, much like what we saw in question 7. So with part A, we're looking at the sum of the arctangent of k plus 1 minus the arctangent of k, and here we're letting k vary from 0 to infinity, okay? So we'll start by just writing out the first few partial sums just to get a feel for what these things will do in terms of that internal cancellation like we saw in question 7. Okay, so here notice that with S2, okay, we lose the arctan of 1, leaving us with arctan 2 minus arctan 0. For S3, we lose arctan 1 and we lose arctan 2, leaving us with the arctangent of 3 minus the arctangent of 0. And S4, okay, we lose arctan 1, arctan 2, and arctan 3, leaving us with just the arctangent of 4 minus arctangent of 0. Okay, so general pattern there, the kth partial sum, and I'm using k here just because that's the letter used for the index in the original series, that's going to equal the arctangent of k minus the arctangent of 0. Okay, now the arctangent of 0 is just 0. And so you see that the kth partial sum is just the arctangent of k. So now to compute the value of this series, we're going to take the limit of the kth partial sum as we let k approach infinity. And so as we saw back in section 9.1 and 9.2, as we let k approach infinity, the arctangent of k will approach pi over 2. Okay, this is a fact from just Calc 1, right? Looking at the arctangent graph, this has a limiting value of pi over 2. So this is a convergent series, and its sum is equal to pi over 2. All right, so now let's look at part B. Really similar, but as we'll see, there is one main difference. So here we're looking at the sum of the natural log of m plus 1 over m, and here m varies from 1 to infinity. Now, to get that cancellation to be seen more clearly, what I'm going to do first is rewrite this quantity natural log of m plus 1 over m using log properties, using the quotient to difference property. And so this is the natural log of m plus 1 minus the natural log of m. All right, so now writing out the first few partial sums, I see cancellation that's really similar to what we saw in part A. Okay, so for S2, we're going to lose the log 2, leaving us with log 3 minus log 1. For S3, we lose log 2 and we lose log 3, leaving us with log 4 minus log 1, so on and so forth. Now notice here the thing we're taking the natural log of first in the simplified expressions is always one more than the index for the partial sum. So for S4, it's log of 5 minus log 1. For S3, it's log 4 minus log 1. So for the mth partial sum, that's going to be log of m plus 1 minus log 1. And here, log 1 is 0, so the mth partial sum is just the log of m plus 1. And so, just like we did in the last example, to compute the sum, we're going to take the limit of the mth partial sum as we let m approach infinity. But here, right, the natural log will blow up if the argument, the thing inside the natural log, is approaching infinity, and that's exactly what's happening here. So we get an infinite limit, right? In other words, this limit of the partial sums does not exist, right? The partial sums are not approaching one specific value, and so for that reason, this series is divergent. Okay, so that's going to do it for this question. I will see you in the next video.